All right, good morning. This is Business Calculus, section 12.1, Local Extrema. Actually, we're only going to do half of it today, a first part of it. We'll do another part tomorrow. This is our first of our lessons on this whole online digital learning thing. So the first thing I'm wanting you to remember is how to tell if a function is increasing or decreasing. And of course, you see in example one right here, the function's increasing where it is going up on the graph from left to right, and is decreasing where it's going down left to right. And of course, they also have a constant part on there. So if they give us a graph, it's so easy to look at the picture and tell, but you need to make sure you know how to write this in the interval notation. So this is increasing on the interval from negative infinity to negative 4, and then again from 4 to 6. So I'm looking at this portion, it's increasing, and then this portion, it's increasing. Notice that it's decreasing on the intervals from negative 4 to 0. So we're talking x negative 4 to x is 0, it's decreasing there. And then again from 6 to infinity, so from there on down. And then it's got that constant part, which is from 0 to 4. So just make sure you just know how to recognize it on a graph and to write it in interval notation. Now, in order to examine the connection between the graph of a function f and the derivative of f, it's sometimes helpful to think of the graph of f as a roller coaster track, with roller coaster car moving from left to right along the graph. So any point along this graph, the floor of that car, which is like a straight line segment, represents the tangent line to the graph at that point. So notice on our picture here, oh, and you can't even see the picture yet. Let me move it up. I feel like it's just like we're at school. So you see how it's going up. There's a positive slope, zero slope at the very tippy top, and then a negative slope on the way down. So the slope of the tangent line changes depending on the position on this curve. What we need to remember is that the slope of a tangent line is actually the derivative. So that comes in handy when we know how to find the derivative, which we did already. So on the back of the page, notice that we have the little box here. If the derivative is greater than 0 for each x in the interval, then that function is increasing on the interval. If the derivative is less than 0, if it's negative on that interval, then f is decreasing on the interval, and then if it's equal to 0, it'd be constant. So let's look at example 2. Find the intervals on which the function here, shown in this graph, is increasing, decreasing, or constant. Now, when we give this a picture, it's so easy to tell when it's increasing and decreasing. Notice we know it's increasing to there. So what is that? This would be just a -1, -2, -3, right? Yeah. And then, so it's increasing, looking at the picture, from negative infinity to -3. And then again from, this would have to be what, x is 1. So that would be from 1 to infinity. It's decreasing in between those two pieces. So that's from -3 to 1. Now, if you remember what we talked about with the derivative, if you find the derivative of that function, then it gives us this function right here, 3x squared plus 6x minus 9. And if you look at its graph, notice it's right here. You see it's a parabola. And if you notice that if you have -3 here and this is 1, notice these portions of the graph are above the y-axis, above 0, right? It's above 0. So we know it's increasing on that part. And then you've got the part in between here that is below the x-axis. So that tells us that it is decreasing on the original function. So if you have the graph, it helps out a lot to be able to relate the derivative graph and the regular function graph. And then it's a little bit easier because you're not having to do all the math to figure out whether it's increasing and decreasing and all that stuff and how, which we're about to do. But the values here that separate these values from that -3 here and that 1, same thing here, the -3 and the 1, these values are critical numbers. That leads us to the next page there. These are critical numbers, and that's where the derivative is either equal to 0 or the derivative doesn't exist. So if we use that information, we can actually do an increasing decreasing test and compute the derivative and find those critical values and then like test our intervals like we did when we did rational inequalities. Then we can figure out which intervals are increasing, decreasing, or constant by using that and not necessarily having a graph, because not everyone's going to be easy to see or easy to figure out what those critical values are. So that's our process there to do that. Now on the next little part, it tells us about peaks and valleys. Now the peaks and valleys are basically our turning points on the graph. The peak would be the highest point in that area. Doesn't have to be the highest point on the graph altogether, but just in that area. And then you've got your low valleys. They don't necessarily have to be the lowest point on the whole graph, but in that little interval it is. So those are called like local maximum or local minimum, that kind of thing. So there's a picture there, show you peaks and valleys. It really makes sense when you look at the picture. So the next little part, that box tells us about local extreme. Local extrema. So you're looking for either a local maximum or a local min. So how do you find that? Well, you're going to be looking for values that are, the highest in an area or the lowest in an area. So if you have a picture like example 3, it's really not bad at all. You identify the locations of this by looking at this picture. So notice it's obvious that the local maximums or local max, that would be what? X sub 1 and X sub 3, this point and this point, right? Those are your local maxes. Those are the highest point in that little area. And then you've got a local min, a local minimum at the point here, X sub 2, and then here, X sub 4. So we're just kind of wanting you to see that it doesn't have to be the highest everywhere. We're not looking at the absolute max right now. We're just looking at the relative max or a local max kind of thing. Now the exact location of these local extremum, rather than like using a calculator to approximate, you can just find the derivative to do it. And you need to find critical points to do that. So if there's an extreme point there, a local max or a local min, that means that that value of x is a critical number. We did that side already. Next page. Okay, so example 4. Example 4, find the critical numbers of the given function. So notice on this one, they gave us the pictures. We're going to use the pictures right now. Starting with example 5, we're actually going to get to the beef of it, the meat of it. We're going to actually work it out. But for here, excuse me, we're going to find the critical numbers of the given functions by looking at the picture. So part A, this one's graphed here. So we can see that this would be, let's see, the top number here. What is that? What do you think that is? This point, that's our, obviously a local maximum, right? And then down here would be a local minimum. So let's see what values that is. Can you kind of see clearly to see what they are? This looks like probably 3, and that's obviously 4. So I believe that would be 4, and that would be 3. So x equal 4, and x equal -3. We're going to verify these in just a bit anyway with our math. Then on part B, critical values here, looking at that picture, this is x cubed. The only one here is actually going to be 0. And I'm going to show you mathematically a little bit how we would come across those values. Then on part C, for this one, looking at that graph, that's an interesting little graph there. You see what it looks like? The only critical value here is going to be this point right there. That's x equals 0 again. And then on part D, looking at this one, this graph is really kind of funky looking. It's kind of hard to tell where that might be, but it actually is 0 because there's this straight piece here, and then the lowest point right there would be 1. So 0 and 1. So I believe after that, does it go to the next example, example 5? Yes, we're going to do example 5. I think I'll put that one on the separate video because I don't want to make this video too very long for you guys. But when you have all those the critical numbers, then to figure out, is it like if you weren't looking at a picture, to figure out if it was a max or a min, then we need to do the first derivative test. Okay, so what we're going to do is pick up with example 5 on that next video.